So in the last few videos, we've been talking about two-level systems, and we've been trying to model the process of absorption and later the process of stimulated emission and spontaneous emission as well, by considering a system which just has two different energy levels, E1 and E2. And we've been saying that initially our electron is in this state. It's in it has energy E1 and it has wave function psi1, which is a function of space and time. And then we were interested in what happens when we apply some light. So how does this electron, which we're guessing it's going to get absorbed and transition up to this energy, which has wave function psi2. And in general, we're interested in how the total wave function of this system evolves as a function of space and time. And that's just a linear combination, we said, of psi1 and psi2. And these coefficients C1 and C2 are functions of time. So C1 is a function of time and C2 is a function of time. And by plugging this into the Schrödinger equation, we found the governing differential equations for this system. And also by figuring out how this light can be modeled quantum mechanically. So light of a specific frequency and with a certain electric field. And the governing equations we got were kind of a mess. I'm just going to write them down here real quick. So we had one equation in terms of the derivative of C1, so e to the minus I omega 1t. And this we said was equal to, now I'm going to write actually everything that's not a function of time in white and everything that is a function of time in red, so that we can clearly see what's going on. So dc1, 1, not 2, dc1 dt e to the minus I omega 1t is equal to, and then we said we had q e naught and then our matrix element psi1 x psi2. And this presumably is just a known value. So this is something that other physicists figure out for us. And then what we need to multiply that by C2, which is a function of time, e to the minus I omega 2t cosine of omega L, which is the frequency of the light, times t. So let's first clean this up a little bit. So I'm going to divide both sides by IH bar. So divide both sides by IH bar. And since all of these things are not a function of time, they're sort of just sitting here. We have to rewrite them over and over again. And so I'm going to call this coefficient A. And I'm just going to say A divided by I so that we don't lump the imaginary number into the coefficient. And if we clean this up a little bit more, just in terms of C1 on the right-hand side, so dc1 dt is just equal to this coefficient, which includes all the non-time dependent stuff, times C2 times e to the I omega 1 minus omega 2 t, and then our cosine, so cosine of omega L t. And that's a little prettier, right? That's less daunting to deal with. And let's make it even prettier. Since we only have now variables in terms of omega 1 minus omega 2, I'm just going to call this delta omega. So it's basically like saying we are only interested in the difference between these two energies. So the difference delta E between these two energies. And delta omega is just delta E over H bar. Okay, so now that we've simplified this, or let's actually replace that with delta omega t. Now that this is simplified, let's write out our other governing differential equation. So in terms of C2, and this is just equal to the same coefficient, so A over I, but now we've got C1, and instead of delta omega t, we've got minus delta omega t, cosine of omega LT. And if you're not convinced, you can do the math yourself to arrive at this equation. And I recommend that you do that. And so this is kind of nasty still. I mean, it's not as bad as it was before, but it's still sort of gross. And so we're going to make an approximation. We're going to say that, okay, well, we know that if we're working with our two-level system, so E2 and E1, and we initially know that the electron is down here, then we know the initial conditions of this system. We know that C1 at time 0 has to be 1 because the electron definitely is in this state, and C2 at time 0 has to be 0. And we're going to say that we're interested in C2 as a function of time, very so close to t equals 0. So we're just going to plug in these initial conditions into our differential equations, and then we're going to solve them. So if you plug in C2 is equal to 0 in this differential equation, you'll see that this whole right-hand side is just equal to 0. So dC1 dt then is just equal to 0. And so it looks like our electrons aren't leaving this state. But in fact, this is just at the very first time step, if you will. So this is, if we're actually going to solve this rigorously, this would be our time step 0. And we'd want to slowly figure out what it is at all times. So this is just the derivative at t is equal to 0. This isn't the derivative at 1 picosecond or 10 picoseconds. And similarly, if we plug in C1 is equal to 1 here, this C1 just goes away. And we've got a differential equation in terms of C2. Just A over, actually, let me rewrite this in red. So dC2 dt is equal to A over I e to the minus I delta omega t times cosine of omega lt. So C2 is in fact changing with time, even at t is equal to 0. And if we let time go for just a little bit, so we evaluate C2 of t by integrating this, then we would need to plug in, C2 would no longer be 0, and we'd have to plug that into our first differential equation. But we're not going to do that. We're just going to assume that C1 as a function of time is just 1. And that's not going to cause too much error, right? That's going to cause a few % error when C1 is like 0.97. And generally this is going to be a very good approximation. So we're just going to roll with it. And also, since this function is no longer a function of space, this is actually a total derivative, not even a partial derivative. So dC2 dt. And so now to finally solve for C2 of t, all we need to do is integrate this differential equation because it's an uncoupled differential equation. It's just in terms of C2 and this function of time over here. So all we need to do is integrate from 0 to, let's say, t prime, just so that we're being mathematically rigorous here, dC2 dt, or d prime, dt prime, plus C2 at 0. So this is C2 for all time. And since C2 at time 0 is just 0, we can ignore this. And all we need to do is perform this integral. So all we need to do is integrate from 0 to t prime, a over I, which we can pull out front, times e to the minus I delta omega t cosine of omega lt. And, well, let's say t prime. And we are integrating actually from 0 to t because we want C2 as a function of t, not t prime. And so you can actually do this integral. It's probably easiest if you expand cosine of omega lt in terms of complex exponentials. So 1/2 e to the I omega lt plus e to the minus I omega lt. And you can do this integral, and you'll end up getting that C2 as a function of time is just equal to negative a over 2 multiplied by this, and then in here we've got our first term. Well, let's actually write that in red because it's going to be a function of time. So e to the I delta omega plus omega L times t, and then minus 1 over delta omega plus omega L. And then we need to add to that e to the minus I, or no, sorry, e to the I delta omega minus omega L. That's where the minus sign was, t. And then minus 1 over delta omega minus omega L. And so this is the result of the integral. So we've actually got now a solution for C2 as a function of time. And we had to make a couple approximations in getting there, and we're going to make some more. So I'm going to say that we're really only interested in frequencies very close to delta omega. So we're only interested in frequencies where omega L is approximately equal to delta omega. And if that's the case, then this term on the right-hand side is much, much larger than this term on the left-hand side, because this has a delta omega minus omega L in the denominator, and this has a delta omega plus omega L. So in general, this term is always going to be smaller. Even if we're not interested in frequencies close to delta omega, this term on the left is always going to be smaller, and often much smaller than this term on the right. And the area under it is going to be considerably smaller. So we're just going to ignore this term on the left-hand side. We're just going to deal with this guy on the right. And then if we do that, and we make some, let's do some further simplification. So let's factor out a complex exponential so we can turn this into a sine. And we're also going to multiply and divide by t over 2. And we're gonna make this equation basically as pretty as we possibly can. And so if you do a bunch of algebra, you'll find that the final equation is just a over 2i. And this equation up here is perfectly valid, but it's not super amenable to further simplification. And so if you do some algebra, you'll get that the final equation, a over 2i e to the I delta omega minus omega, actually let me rewrite this in red, e to the I delta omega minus omega L t times t times sinc of delta omega minus omega L over 2 times t. And this is my personal favorite form of this equation because it's going to allow us to make some more assumptions and simplify this even further. But this is it. We've done it. We've found an expression for C2 as a function of time. So we've gone from basic quantum mechanics and used a two-level model, so just two different energy levels, and we figured out what the how the wave functions evolve with time. So if this is our electron, that's initially in state 1, and then we apply some light to it of frequency h bar omega and electric field E naught, which is wrapped into this A term, then we know how this how the wave function of this electron is going to evolve. And in the next couple of videos, we're going to interpret this. So we're going to interpret this not in terms of quantum mechanics, but in terms of macroscopic quantities. So in terms of macroscopic quantities, like recombination, which has some rate per unit volume. Oh, sorry, this should be a t over 2 up here. I just realized that mistake. So I hope you enjoyed the video. If you did, please give it a like and subscribe to my channel. If you have any questions or comments, please feel free to post them down below. And again, this was an intensely mathematical video, so I expect you will have questions. It took me quite a long time to figure out all this math myself. So don't feel bad if it takes you a while too. And thanks for watching. I'll see you next time.